Tonight, we'll be exploring some of the most extreme events that we have ever discovered in our cosmos. These are moments when the universe is pushed to its most powerful limits, and ordinary astronomy gives way to some of the most dramatic processes known to science. Across the cosmos, immense forces can transform entire regions of space in barely an instant. Some events release energy on scales too vast to imagine, while others reveal conditions that seem too extreme to even exist. What makes them so fascinating is that they are not simply destructive. Many of these events also reshape their surroundings and leave behind clues that scientists can study for millions of years. By following those clues, we can learn how matter behaves when gravity becomes overwhelming, or when stars reach the final stages of their lives. Even now, astronomers are detecting new signals from events that happened billions of years ago. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, there's nothing you need to do but relax. Let your shoulders soften, allow your breathing to slow, and as your mind begins to gently unwind, join me as we explore these extraordinary cosmic events together. Let's begin. A supernova can briefly outshine every star in its entire galaxy. For a short time, one dying star can become the brightest object across a system containing billions of suns. The explosion happens when a star reaches a point where its structure can no longer remain stable. In certain supernovae, the core collapses under gravity, and the outer layers are blasted outward at tremendous speed. The sudden release of energy can make the star shine billions of times more brightly than it did before. From another galaxy, that single point of light may become visible beside the combined glow of the entire stellar population around it. The brilliance does not last. It rises rapidly, then fades over weeks or months as the expanding debris cools. Yet during that brief interval, astronomers can detect the explosion across enormous cosmic distances. Supernovae have appeared unexpectedly in galaxies that seemed completely ordinary only days earlier. A star that may have gone unnoticed for millions of years can suddenly dominate its galaxy, then disappear forever as a recognizable star. Colliding neutron stars can forge gold heavier than several planet Earths. Gold can be made in an event so violent that two dead stars have to crash together. Neutron stars are the compressed remains of massive stars. When two of them orbit one another, they gradually lose energy until their separation becomes smaller and smaller. Eventually, they collide. The impact throws intensely neutron-rich material into space, where atomic nuclei can capture neutrons at extraordinary rates. This process can build some of the heaviest naturally occurring elements in the periodic table. In a single merger, the total quantity of freshly produced heavy elements can be astonishing. Models of observed collisions suggest that the amount of gold alone may reach several times the mass of Earth, although the exact yield varies from event to event. That material does not remain gathered in one place. It expands into space and eventually mixes with gas that may later form new stars and planets. The golden jewelry on Earth therefore carries a remarkable possibility. Some of its atoms may have been created during a collision between two ancient stellar remnants. Black holes can tear whole stars apart before swallowing their remains. A star does not need to cross a black hole's boundary to be destroyed. If it passes close enough, the difference in gravity between the star's near side and far side can become overwhelming. Those tidal forces stretch the star until its own gravity can no longer hold it together. The result is a tidal disruption event. Instead of falling inward as a complete object, the star is pulled into streams of extremely hot gas. Some of that material escapes on long trajectories. The rest swings back toward the black hole and begins forming a rapidly moving disk. As the gas collides and heats, it can release an enormous burst of radiation that makes a previously inactive galactic center suddenly flare. Astronomers have discovered these events by watching galaxies brighten where no ordinary star could explain the change. The black hole itself remains dark. What becomes visible is the destruction happening around it. By studying the flare, researchers can investigate black holes that might otherwise reveal almost nothing about their presence. Some gamma-ray bursts release more energy than the sun ever will. The most powerful flashes of gamma radiation can release an extraordinary amount of energy within seconds. The sun will shine for roughly 10 billion years during its main lifetime, steadily converting hydrogen into helium and radiating energy into space. A gamma-ray burst can rival or exceed that lifetime output in an astonishingly short interval, especially when astronomers calculate the apparent energy along the narrow direction of its beam. These bursts are not ordinary stellar explosions viewed from farther away. They are highly concentrated events associated with collapsing massive stars or merging compact objects. Much of their radiation can emerge through tightly focused jets, moving at speeds extremely close to that of light. If one of those jets points toward Earth, the event appears spectacularly bright even from billions of light years away. The burst may be over before a telescope can turn toward it. Automated spacecraft therefore watch the sky continuously and send alerts within moments. What follows can reveal an explosion that briefly became one of the most energetic observable events anywhere in the universe. Neutron stars pack more than a sun inside a city-sized sphere. Take more mass than the sun contains and compress it until the resulting object is only about the size of a large city. That is the scale of a neutron star. These objects form when the core of a massive star collapses after nuclear reactions can no longer support it. Gravity crushes ordinary atomic structure so severely that matter enters a state found nowhere naturally on Earth. The resulting star may measure only around 20 kilometers across, yet it can contain well over 1 solar mass. Its surface gravity is therefore extraordinary. An object dropped nearby would accelerate with a force vastly greater than anything experienced on our planet. The escape speed is also a substantial fraction of the speed of light. Despite this compactness, neutron stars are not black holes. Light can still escape from their surfaces, allowing astronomers to study their heat and rotation. They occupy a remarkable middle ground in nature, where familiar matter has been compressed almost as far as possible without disappearing behind an event horizon. Two merging black holes can shake the fabric of spacetime itself. When black holes orbit each other, they do something that cannot be seen with ordinary light. Their motion distorts spacetime and sends ripples outward at the speed of light. These ripples are gravitational waves. At first, the black holes may circle one another slowly. Over time, they radiate energy away through those waves, causing the orbit to shrink. The final moments become extraordinarily rapid. The two objects whirl together faster and faster until their horizons merge and a single larger black hole remains. The changing gravitational field launches a characteristic signal across the universe. By the time that signal reaches Earth, it has stretched and squeezed distances by less than the width of a proton across kilometer-scale detectors. Yet instruments can measure it. The first direct detection announced in 2016 came from two merging black holes more than 1 billion light-years away. Nothing traveled from the collision to shake Earth mechanically. Instead, the geometry of space itself changed by an almost unimaginably tiny amount as the wave passed through. A nearby stellar explosion may have altered life on ancient Earth. Earth has been exposed to exploding stars before, and traces of at least some nearby events appear to remain on our planet. Scientists have discovered deposits of Im-60, a radioactive isotope that is difficult to produce naturally on Earth in significant amounts. It has been found in ancient seafloor material and other geological samples. The best explanation is that debris from supernova reached the solar system millions of years ago and settled onto Earth. These explosions were not close enough to sterilize the planet, but researchers continue investigating whether they affected the atmosphere or climate. Increased high-energy radiation could potentially change atmospheric chemistry and raise radiation exposure at the surface. Exactly what biological consequences followed remains uncertain, and no dramatic extinction has been conclusively tied to these particular events. What makes the evidence extraordinary is its physical connection to vanished stars. Material created during distant explosions appears to have crossed interstellar space before becoming part of Earth's geological record. Our planet has therefore preserved particles from cosmic catastrophes that occurred in our galactic neighborhood. Magnetars produce magnetic fields trillions of times stronger than Earth's. Magnetars are neutron stars with magnetic fields so intense that everyday comparisons quickly become inadequate. Earth's magnetic field is strong enough to guide compass needles and help shield the planet from charged particles. A magnetar can exceed it by trillions of times. The field near its surface is powerful enough to influence atoms in ways that ordinary terrestrial magnetism never could. Electrons behave differently under such conditions, and the structure of matter itself can be distorted. These fields are thought to arise from extreme conditions during the neutron star's formation, although the precise details remain an active area of research. Magnetars are usually discovered because they produce bursts of X-rays or gamma rays, rather than because their magnetism can be measured directly from nearby. Some rotate only once every few seconds, which is relatively slow for a neutron star. Yet enormous magnetic energy remains stored around them. As that field evolves and stresses the solid crust, sudden rearrangements can release powerful flashes that briefly make a distant magnetar one of the brightest high-energy objects in the sky. Certain stars explode so completely that no remnant survives afterward. Most stellar explosions leave something behind. A collapsed core may become a neutron star, while an even heavier one can form a black hole. But some exceptionally massive stars may end in a different way. Under the right internal conditions, extremely energetic photons begin producing pairs of particles and antiparticles. That change removes pressure that had been helping support the star against gravity. The core contracts, temperatures rise, and oxygen burning can suddenly race out of control. Instead of merely blowing away the outer layers, the thermonuclear explosion can disrupt the entire star. Nothing compact remains at the center. No neutron star survives, and no black hole is immediately formed from the destroyed core. This predicted event is called a pair instability supernova. Astronomers have searched for possible examples by studying unusually luminous explosions and their chemical signatures. The required stars are thought to be uncommon in the modern universe. They may have been more important much earlier, when stars could form from gas containing far fewer heavy elements than the material available in galaxies today. The universe still carries gravitational echoes from collisions billions of years ago. A violent collision can end long before its gravitational waves finish traveling through the universe. Once created, those waves continue moving outward at the speed of light. They weaken with distance, yet they do not simply vanish when the objects that produced them disappear from view. This means detectors on Earth can register events that happened before our planet even existed in its present form. When a distant pair of black holes merges, the gravitational signal begins crossing intergalactic space while galaxies continue evolving around it. Billions of years later, that distortion may finally pass through Earth. Instruments record only a fraction of a second or a few seconds of the strongest signal, but hidden inside it is information about the original system. Scientists can estimate the masses of the black holes and how rapidly they were moving before merger. In this sense, gravitational wave astronomy does not observe the universe as it is now. It listens to physical disturbances that have been traveling toward us since unimaginably ancient cosmic events. Supernova shock waves can race through space at millions of miles per hour. The expanding debris from a supernova does not drift gently away from the destroyed star. It can blast outward at thousands of kilometers per second, carrying an immense shockwave into surrounding space. That moving front slams into gas that may have been sitting almost undisturbed for ages. Particles are heated to temperatures high enough to produce X-rays, while magnetic fields become compressed and tangled. Over time, the shock slows as it sweeps up increasing amounts of interstellar material. The remains can still span many light years and stay visible for thousands of years. Famous supernova remnants such as Cassiopeia A allow astronomers to watch this process unfolding long after the original explosion. Different elements glow at different wavelengths, revealing how the stellar interior was thrown outward. The shock is therefore more than the aftermath of a blast. It becomes a moving laboratory where matter is heated, accelerated and rearranged under conditions impossible to reproduce on the same scale on Earth. A star's death can continue disturbing its neighborhood for generations of human history. One famous supernova remained visible during daylight for several weeks. In the year 1054, observers saw a new light appear in the sky that was bright enough to be noticed during the day. Chinese records describe a guest star near the constellation now called Taurus. It remained visible in daylight for more than 3 weeks and could be seen at night for much longer. At the time, nobody understood that they were witnessing the death of a distant star. Nearly 1,000 years later, astronomers connected those historical observations with the Crab Nebula. The expanding cloud occupies the same region of the sky and contains a rapidly rotating neutron star at its center. Modern measurements of the nebula's motion also point back toward the same era. This makes the event an extraordinary meeting between written history and astrophysics. People living long before telescopes recorded a stellar explosion with their own eyes, and those observations still help scientists study the remnant today. A brief celestial surprise seen by medieval skywatchers became one of the most important supernova remnants in modern astronomy. A collapsing stellar core can rebound in less than 1 second. The center of a massive star can spend millions of years evolving, then undergo catastrophic change almost instantly. Near the end of its life, the core becomes dominated by iron. Fusing iron cannot provide the energy needed to support the star, so gravity finally wins. The core collapses at tremendous speed. Electrons are driven into protons, helping create neutrons while enormous numbers of neutrinos are produced. As the inner region reaches nuclear density, matter suddenly becomes far more resistant to further compression. The collapse halts abruptly and the inner core rebounds. This entire transformation can unfold in well under a second. What happens next is remarkably complicated. A shock wave moves outward, but it can lose energy and store. Neutrinos streaming from the newly formed compact core may help revive it, allowing the explosion to develop. Researchers still use powerful computer simulations to understand exactly how this works in different stars. A supernova may shine for months, yet the decisive collapse that begins the event can happen faster than a human heartbeat. Some dying stars explode only after stealing matter from a companion. Not every supernova begins with a single massive star collapsing under its own weight. A white dwarf can spend billions of years in relative stability before a nearby companion changes its fate. White dwarfs are dense stellar remnants left behind by stars that were not massive enough to undergo core collapse. In a close binary system, gravity can draw gas from the companion onto the white dwarf. As the remnant gains material, its internal conditions can become increasingly extreme. If carbon fusion ignites explosively through much of the star, a thermonuclear supernova may follow. The white dwarf is torn apart rather than leaving a conventional neutron star behind. These explosions are known as Type ER supernova. The exact paths that trigger them are still debated, because some may involve two white dwarfs rather than steady feeding from an ordinary companion. What remains remarkable is the delay. A star can appear to have ended its active life long ago, then become the center of a brilliant explosion because another star in the same system alters its future. Astronomers use certain supernovae to measure the universe's accelerating expansion. Some stellar explosions have become tools for measuring distances across billions of light years. Type IR supernova are especially valuable because their brightness can be standardized using the way their light rises and fades. If astronomers know how luminous an explosion really was, they can compare that with how faint it appears from Earth and estimate its distance. During the late 20th century, teams studying distant Type Ia supernova expected to measure how gravity had slowed cosmic expansion. Instead, the explosions appeared dimmer than anticipated for a universe decelerating in the expected way. The evidence pointed towards something astonishing. Cosmic expansion had begun accelerating. This discovery transformed modern cosmology and led to the concept commonly called dark energy, which describes the unknown cause of that acceleration. The supernova did not explain what dark energy actually is. They revealed its effect. By studying dying stars in distant galaxies, astronomers uncovered a change in the behavior of the universe on the largest possible scale. Stellar destruction became a ruler for cosmic history. The first elements heavier than iron were created during cosmic catastrophes. Ordinary stellar fusion has a natural limit. Stars can build increasingly heavy nuclei in their interiors, but producing elements beyond iron through normal fusion no longer releases useful energy. To create many heavier elements, nature needs environments packed with free neutrons and enormous amounts of energy. Some of those conditions occur during explosive stellar events. Rapid neutron capture allows atomic nuclei to absorb neutrons faster than they can decay, building extremely heavy forms of matter that later transform into stable elements. This mechanism is known as the R process. Modern evidence shows that neutron star mergers are major sites for it, while certain rare stellar explosions may also contribute. The exact history of where different heavy elements originated remains an active field of research. What is clear is that much of the periodic table could not have been assembled through calm stellar burning alone. Some atoms required cosmic emergencies. Material later incorporated into planets was enriched by catastrophic events that occurred before the solar system formed. The chemistry of ordinary matter therefore carries a record of ancient violence. Supernova remnants can continue expanding for tens of thousands of years. A supernova may be brief, but its physical footprint can survive through vast stretches of time. After the initial explosion, stellar debris expands into surrounding interstellar gas and gradually forms a supernova remnant. During its early stages, the ejecta move outward rapidly and begin sweeping up material. Eventually, the amount of captured gas becomes greater than the original mass thrown from the star. The remnant then enters a slower phase in which its shock continues expanding while losing energy. Over tens of thousands of years, the structure can spread across dozens of light years. Its appearance also changes dramatically. Young remnants may glow strongly in X-rays because their gas is extremely hot. Older remnants can become large optical shells traced by filaments of cooler material. Eventually, the boundary becomes difficult to distinguish from the interstellar medium around it. By then, the exploded star has effectively mixed part of itself into the galaxy. Long after the flash has vanished, its expanding remains continue transporting matter and energy through the space between other stars. The Crab Nebula surrounds a star that exploded nearly a millennium ago. At the center of the Crab Nebula sits a tiny remnant whose behavior is almost as remarkable as the explosion that created it. The Crab Pulsar is a neutron star rotating around 30 times every second. Each turn sweeps beams of radiation through space, producing pulses detected across several wavelengths. Those pulses are so regular that astronomers can monitor tiny changes in the star's rotation with remarkable precision. Around it lies a glowing nebula several light years across. The pulsar continuously releases a wind of energetic particles that crashes into the surrounding material and helps power the nebula's distinctive radiation. Detailed images reveal structures that change over surprisingly short timescales, including moving wisps near the central star. The system therefore allows astronomers to study both the aftermath of the ancient supernova and the continuing activity of the object left behind. The explosion happened in historical times, but its engine is still running. Nearly 1,000 years later, the collapsed core continues injecting energy into the debris that once belonged to its parent star. Ancient observers recorded stellar explosions long before telescopes existed. Some of the earliest useful supernova observations were made with nothing more than careful human eyesight. Astronomers in several historical cultures watched the sky closely enough to notice when a bright new point suddenly appeared where no star had been recorded before. Chinese court astronomers were particularly systematic. Their records of guest stars sometimes included where the object appeared, how bright it looked, and how long it remained visible. These descriptions can now be compared with known supernova remnants. In several cases, the connection is convincing enough to give modern researchers an approximate explosion date. That historical information matters because the age of a remnant helps scientists calculate how quickly its debris has expanded and how its brightness has changed. Written observations made for entirely different reasons have therefore become scientific data centuries later. They also reveal something deeply human about astronomy. Long before anyone understood stellar evolution, people recognized that the supposedly unchanging heavens could produce sudden new lights. Their records preserved events whose physical remains are still being studied with modern observatories. Some supernovae shine unusually brightly because magnetars power them from within. A supernova can receive a second source of energy after the initial explosion has already begun. In some extraordinarily luminous events, astronomers suspect that the newly formed neutron star is a rapidly spinning magnetar. At birth, such an object can rotate far faster than most magnetars observed later in life. It also contains an immense reservoir of rotational energy. As its powerful magnetic field slows the spin, some of that stored energy can be transferred into the expanding supernova debris. The surrounding material absorbs the added power and radiates it outward, keeping the explosion brighter than radioactive decay alone would normally allow. This idea helps explain a class known as superluminous supernova, which can greatly exceed the brightness of more familiar stellar explosions. Scientists test the model by comparing observed light curves with predictions for spinning magnetars. Other mechanisms may contribute in some cases, so the picture is still developing. Yet the possibility is remarkable. The compact object born inside an explosion may immediately begin powering the very debris created during its own formation. Pair instability supernova may destroy stars hundreds of times heavier than the Sun. Some of the largest stars ever formed may die without leaving any central remnant at all. Deep inside an exceptionally massive star, temperatures can become so extreme that energetic photons begin turning into pairs of particles. This removes radiation pressure from the core at exactly the wrong moment. Gravity suddenly gains the advantage, forcing the interior to contract and heat even further. Oxygen then begins burning at a runaway rate. Instead of producing a normal collapse, the resulting thermonuclear reaction can release enough energy to reverse the contraction and blow the entire star apart. Astronomers call this a pair instability supernova. The process is expected only within a particular range of stellar masses, especially in stars containing relatively few heavy elements. Such giants may have been more common in the early universe. Their explosions would have scattered enormous quantities of newly formed elements into surrounding space. Finding a convincing example today would give astronomers a rare chance to witness a stellar death so complete that the original star is physically erased. Failed supernovae may vanish quietly as their stars collapse into black holes. A massive star does not always announce its death with a brilliant explosion. In some cases, the core may collapse so powerfully that the outward blast never succeeds. The star begins the same catastrophic process that can create a supernova, but the shock loses its struggle against gravity. Material continues falling inward until a black hole forms. If most of the star follows, the expected explosion may never appear. Astronomers have searched for these failed supernovae by repeatedly photographing large numbers of massive stars in nearby galaxies. The strategy is wonderfully simple. Find a luminous star, keep watching it, and ask whether it eventually disappears without producing the expected final flash. Several intriguing candidates have been identified. One red supergiant appeared to brighten modestly before fading dramatically from view. Dust can complicate such observations, so proving a direct collapse is difficult. If these silent deaths are common, they could explain why astronomers observe fewer ordinary supernovae from the most massive stars than simple stellar evolution models once predicted. A supernova can compress surrounding gas and trigger entirely new stars. The death of one star can help create the next generation. When a supernova shockwave sweeps through a nearby molecular cloud, it suddenly places cold interstellar gas under intense pressure. Regions that were previously too diffuse to collapse may become squeezed until gravity begins pulling them together. Dense pockets can then fragment into smaller clumps, eventually forming protostars. The process does not happen after every supernova because the timing and distance have to be favorable. A shock that is too strong may simply tear a cloud apart, while one that has weakened too much may barely disturb it. Yet observations of expanding bubbles and star-forming regions suggest that triggered star birth can occur around energetic stellar feedback. The newborn stars may even contain material expelled by the original explosion. This creates a remarkable cycle. One generation of stars ends by violently rearranging the gas around it, and that disturbance can help assemble another generation. Stellar death is therefore not simply an ending. Under the right conditions, it can become part of the machinery that begins new suns. Shocked atoms inside supernova remnants can glow brightly in invisible X-rays. Much of a supernova remnant's most dramatic light cannot be seen by human eyes. When the expanding blast wave strikes surrounding gas, particles are heated to temperatures of millions of degrees. At those temperatures, atoms lose many of their electrons and become highly ionized. As electrons move between energy states or collide with other particles, the hot plasma produces X-rays. Space telescopes can separate this radiation into different energies and reveal which elements are present. Oxygen may dominate one region, while silicon or iron appears elsewhere. These maps allow astronomers to reconstruct how the destroyed star was layered before it exploded. They can even trace knots of material that were launched in different directions. X-ray images of remnants such as Cassiopeia, a look completely different from ordinary visible light photographs because they reveal the hottest components of the wreckage. The colors used in published images are usually assigned to different energy bands rather than showing what an eye would see. They transform invisible radiation into a detailed map of the stellar interior that no longer exists. Radioactive elements keep many supernovae shining long after the initial explosion. The first flash of a supernova is not the only reason it remains bright. Inside many explosions, enormous temperatures create unstable radioactive isotopes. One especially important example is nickel-56. It decays into cobalt-56, which later decays into stable iron-56. Each step releases energy in the form of particles and high-energy radiation. The expanding debris absorbs much of that energy and converts it into visible light. This radioactive heating can sustain the glow for weeks or months after the original shock has passed through the star. Astronomers study how the brightness declines because the pattern reveals which isotopes are powering the fading remnant. The amount of nickel produced also tells them about conditions during the explosion itself. In some supernova, radioactive decay dominates the later light curve so clearly that the physics of unstable nuclei becomes visible across another galaxy. A handful of atoms changing their internal structure would seem insignificant. Multiplied across a vast cloud of stellar debris, the same process can illuminate space long after the star's violent destruction has ended. Neutrinos escape collapsing stars before visible light reaches the surface. When the core of a massive star collapses, one of the earliest warnings can arrive in particles that pass almost effortlessly through matter. Neutrinos interact so weakly that trillions move through your body every second without leaving any noticeable trace. During stellar collapse, however, they are produced in astonishing numbers. The newly forming compact core releases a huge burst of them as matter is compressed, and nuclear reactions change protons and electrons. Because neutrinos can pass through the overlying star much more readily than photons, they escape before the visible explosion reaches the surface. Light still has to wait for the shockwave to travel outward through the star's layers. For a nearby supernova, neutrino detectors on Earth could therefore register the event before telescopes see the star brighten. Automated alert systems already exist to take advantage of this possibility. A sudden burst could give astronomers valuable time to turn instruments toward the correct region of sky. The universe may effectively whisper that a star has collapsed before the heavens visibly announce it. Scientists detected neutrinos from a supernova outside the Milky Way. In February of 1987, detectors deep underground recorded something extraordinary. A small burst of neutrinos arrived from the direction of the Large Magellanic Cloud. Hours later, astronomers were watching a supernova there that became known as Supernova 1987A. Only about 24 neutrinos were detected across several experiments, yet those few particles transformed astrophysics. They had traveled roughly 160,000 years through space before reaching Earth. Their arrival confirmed a central prediction about core-collapse supernova. Most of the gravitational energy released during the collapse emerges as neutrinos rather than visible light. The observation also allowed researchers to test how these elusive particles behave across an enormous distance. It remains the only supernova from which neutrinos have been directly detected so far. Modern detectors are much larger and more sensitive, so another sufficiently nearby stellar explosion could produce thousands of signals. The next burst would let scientists examine the hidden core of a collapsing star in detail that optical telescopes alone could never provide. Some stellar explosions leave rapidly spinning neutron stars called pulsars. After certain massive stars explode, their crushed cores can become cosmic beacons. A pulsar is a rotating neutron star whose magnetic axis is usually tilted away from its spin axis. Charged particles accelerate around the magnetic poles and produce beams of radiation. As the star turns, those beams sweep through space. If one crosses Earth, telescopes detect a pulse each time the star completes a rotation. The effect resembles a lighthouse, although nothing is literally switching on and off at the source. The beam is simply moving past us. Pulsars were discovered in the late 1960s when radio astronomers noticed signals repeating with astonishing regularity. The first source was so unexpected that researchers briefly considered whether an artificial transmission might be responsible. Nature soon provided the answer when more examples appeared. Today, thousands are known. Their timing is so precise that astronomers can use them to investigate gravity, map interstellar plasma, and study unseen companions. A star can therefore die explosively and leave behind something that behaves like one of the universe's most accurate natural clocks. Pulsars can sweep radio beams across Earth with clock-like precision. Some pulsars are so regular that the arrival times of their signals can be predicted with remarkable accuracy. Each radio pulse may look simple, but it comes from an object rotating in a stable rhythm across enormous spans of time. Astronomers measure when individual pulses reach Earth and compare them with a mathematical timing model. Tiny departures can reveal extraordinary things. A pulsar may be orbiting another star, moving through curved spacetime, or experiencing subtle changes in its own rotation. Even planets have been discovered around pulsars because their gravity shifts the neutron star back and forth enough to alter the timing. The first confirmed planets outside our solar system were found this way. Interstellar gas also affects the pulses because different radio frequencies travel through ionized material at slightly different speeds. Correcting for that delay gives information about matter between the stars. A seemingly repetitive signal therefore becomes a precision experiment stretching across light years. Every pulse carries not only the rhythm of the neutron star, but also evidence about whatever has influenced its journey toward Earth. The fastest known pulsars complete hundreds of rotations every second. A neutron star can spin so quickly that its surface travels through space at a significant fraction of light speed. The fastest confirmed pulsars rotate more than 700 times each second. These objects are called millisecond pulsars because a complete turn takes only a few thousandths of a second. They were not necessarily born spinning this rapidly. Many appear to have been accelerated later by stealing gas from a companion star. As matter spirals inward, it transfers angular momentum to the neutron star and gradually spins it up. This recycling process can transform an older pulsar into an exceptionally stable rapid rotator. There is a physical limit to how fast such a star can turn. If rotation became extreme enough, material at the equator would no longer remain gravitationally bound. Measuring the fastest pulsars therefore helps scientists investigate the strength and internal structure of neutron stars. Their rotation pushes matter toward conditions that laboratories cannot approach. Something heavier than the Sun can whirl hundreds of times per second without tearing itself apart. Neutron star crusts may be the strongest known material in nature. The outer solid layer of a neutron star is unlike any crust found on a planet. Gravity compresses atomic nuclei into structures packed at extraordinary density, while electrons move through the material under immense pressure. Computer simulations suggest that this nuclear crust may be around 10 billion times stronger than steel when compared by breaking strain. That does not mean a piece could simply be brought to Earth and used as construction material. Neutron star matter exists only because crushing gravity maintains those conditions. Remove it from that environment, and it would change catastrophically. The strength matters because a rotating neutron star can support tiny distortions rather than becoming perfectly spherical. Those distortions may generate continuous gravitational waves if the star spins rapidly enough. The crust can also store stress produced by changes in rotation or magnetic fields. Eventually, it may fail suddenly. Understanding how it breaks helps researchers interpret abrupt behavior seen in neutron stars. The strongest known material in the universe may therefore reveal itself not through something we can touch, but through distant stars trembling under their own impossible weight. Mountains on neutron stars may rise only millimeters above their surfaces. On Earth, gravity allows mountains to tower kilometers above sea level. On a neutron star, gravity is so overwhelming that even the strongest crust can support only tiny irregularities. What astronomers casually call a mountain might rise mere millimeters or centimeters above the average surface, depending on the star and the crust's strength. That sounds almost perfectly smooth, but the distortion can still matter. A neutron star contains more than a solar mass, so even a microscopic departure from perfect symmetry involves an enormous amount of matter. If the star rotates rapidly, such a bump could make its gravitational field vary slightly with every turn. In principle, that creates a continuous stream of gravitational waves. Detectors are searching for these faint signals from known pulsars. A successful detection would reveal information about the star's interior and show how much strain its crust can actually endure. The scale is wonderfully counterintuitive. A feature too small to step over on Earth could become astrophysically significant when attached to one of the densest objects in existence. A teaspoon of neutron star matter would weigh billions of tons. The enormous density of neutron stars comes from what happens when atoms are crushed beyond their familiar form. In ordinary matter, most of an atom's volume is effectively empty space between its tiny nucleus and surrounding electrons. During stellar collapse, pressure becomes so intense that electrons are forced much closer to nuclei. Many combine with protons through nuclear reactions that produce neutrons. The resulting material is packed at densities similar to those inside atomic nuclei. A teaspoonful is often estimated to have a mass of billions of tons. Such a sample could never simply sit on a kitchen table. Outside the neutron star's crushing gravity, the material would not remain in the same state. The comparison is useful because it shows how dramatically stellar collapse changes matter. A neutron star achieves this density across an object many kilometers wide. Its tremendous mass is not hidden inside a tiny central point. The entire interior is compressed into exotic phases that physicists are still trying to understand. Familiar atoms have effectively been pushed to the limit of what ordinary matter can endure. Pulsar glitches occur when neutron stars suddenly spin slightly faster. Pulsars usually slow down very gradually as they lose rotational energy. Every so often, however, some of them do the opposite. Their spin rate suddenly jumps upward by a tiny amount. Astronomers call this a glitch. The change may be minuscule, yet precision timing makes it unmistakable. One leading explanation involves superfluid material inside the neutron star. This fluid can rotate through microscopic vortices that behave differently from the solid crust surrounding them. As the outer star slows, some internal vortices may remain temporarily pinned in place. A growing difference develops between the rotation of the crust and the hidden fluid beneath it. Eventually, large numbers of vortices can shift suddenly and transfer angular momentum outward. The crust responds by spinning faster. Afterward, the pulsar gradually adjusts toward its previous trend. Glitches provide one of the rare ways to probe processes deep inside neutron stars. Scientists cannot see those interiors directly, but a tiny change in timing can reveal that enormous reservoirs of quantum fluid are moving beneath the surface of a distant collapsed star. Starquakes can crack magnetar crusts and unleash enormous bursts of radiation. A magnetar's magnetic field does not remain perfectly static. As it changes, it can twist and strain the solid crust beneath the surface. The crust may resist for years before suddenly shifting or fracturing. That abrupt rearrangement is often described as a starquake. Unlike an earthquake, the disturbance occurs on an object whose gravity and magnetic field dwarf anything found on our planet. The quake can alter magnetic structures outside the star and accelerate enormous numbers of particles. Energy then erupts as X-rays or gamma rays. Some bursts last only fractions of a second, while rarer giant flares release vastly more power. Astronomers infer the connection between crustal stress and magnetic activity by studying how bursts cluster and how a magnetar's rotation changes during active periods. The details remain complex because events inside the star and changes in its external magnetic field can influence each other. What begins as stress in a rigid crust only kilometers across can become a flash visible from across the galaxy. A microscopic fracture can have astronomical consequences. A powerful magnetar flare once disturbed Earth's upper atmosphere. On December 27, 2004, an enormous pulse of gamma rays swept across the solar system. It came from a magnetar known as SGR 1806-20, located tens of thousands of light-years away. The first fraction of a second was so intense that several spacecraft detectors were overwhelmed. Even at that extraordinary distance, the radiation reached Earth strongly enough to affect the ionosphere. This upper region of the atmosphere contains charged particles and normally responds most noticeably to solar activity. For a distant neutron star to alter it demonstrates the astonishing power of the flare. The event was followed by a fading signal whose changing brightness reflected the rotation of the magnetar. Researchers concluded that an enormous rearrangement of magnetic energy had taken place. Had the same flare occurred much closer, its effects would have been far more severe. Instead, Earth received a harmless but measurable disturbance from the other side of the Milky Way. A star only kilometers wide briefly reached across a substantial fraction of our galaxy and touched the atmosphere above us. Magnetars may be born when exceptionally fast stellar cores collapse. Why some neutron stars become magnetars while others do not remains one of their central mysteries. One influential idea begins during the final moments of the parent star. If the collapsing stellar core is rotating extremely quickly, violent motions in the newly formed neutron star may amplify magnetic fields through a dynamo process. Similar principles operate in other astrophysical objects, but the conditions here are vastly more intense. Convection, rotation, and electrically conducting matter could work together to build a magnetic field of extraordinary strength within seconds. Other theories suggest that some parent stars already possess unusually strong magnetic fields that become greatly intensified during collapse. Observations provide clues, but no single explanation has settled the question. Astronomers compare magnetars with ordinary pulsars and study the star clusters where some of them were born. They also examined supernova remnants for evidence about the original explosion. The answer matters because magnetars represent a rare path through stellar evolution. Two massive stars may begin with broadly similar ingredients, yet one leaves an ordinary neutron star, while another creates the most magnetic object known. Neutron stars can cool from billions of degrees surprisingly quickly. A newborn neutron star begins life unimaginably hot. Immediately after collapse, its interior can reach temperatures of tens or hundreds of billions of degrees. Yet it sheds heat far more efficiently than an ordinary glowing object. During the earliest stages, much of the cooling occurs through neutrinos produced deep inside the star. These particles escape with energy that would otherwise remain trapped as heat. Over thousands of years, the surface temperature falls dramatically, although the star can still remain hot enough to shine strongly in X-rays. The exact cooling rate depends on what matter exists in the interior. Certain nuclear reactions may produce neutrinos very efficiently, while superfluid phases can change how heat moves and how particles interact. Astronomers therefore compare the measured temperatures of neutron stars with estimates of their ages. A star cooling faster or slower than expected can reveal hidden physics occurring kilometers beneath an inaccessible surface. Temperature becomes a diagnostic tool. Watching a dead star lose its heat can tell researchers what forms of matter may exist at densities no experiment on Earth can reproduce. Superfluid matter may flow without friction inside neutron star interiors. Deep inside a neutron star, matter can enter a quantum state with no everyday equivalent at human scale. Under enormous pressure and at sufficiently low temperatures, neutrons are expected to pair up and form a superfluid. A superfluid can move without the ordinary viscosity that slows normal liquids. Similar behavior has been created in laboratory systems at extremely low temperatures, but neutron stars provide a natural version involving nuclear matter under crushing density. The superfluid does not simply swirl like water inside a container. Its rotation is organized into quantized vortices. Each vortex carries a fixed amount of circulation, and vast numbers of them thread through the interior of a spinning star. Their interactions with the crust and other components may influence sudden changes in pulsar rotation. Superfluidity also affects heat capacity and neutrino emission, so it can change how neutron stars cool. Astronomers have even interpreted temperature changes in some young neutron stars as possible evidence that superfluid transitions are occurring. Quantum mechanics may therefore control the behavior of matter across an entire stellar remnant. Nuclear pasta may form bizarre structures beneath neutron star crusts. Just before the solid crust gives way to the deeper interior of a neutron star, matter may organize itself into shapes that physicists jokingly named after food. At these densities, two powerful influences compete. Nuclear forces try to bind protons and neutrons together, while electrical repulsion pushes positively charged regions apart. The compromise may produce sheets, rods, and tangled structures rather than neat spherical nuclei. Researchers use names such as lasagna and spaghetti because the simulated shapes resemble familiar pasta. The humor hides serious physics. Nuclear pasta could be among the strongest material configurations in the universe. It may influence how heat travels through the crust and how the star's magnetic field evolves. Its structure could also affect neutrino interactions and the behavior of matter during neutron-star mergers. No scientist can collect a sample, so the evidence comes from theoretical calculations and sophisticated simulations. A region only a short distance beneath a neutron star's surface may contain matter arranged into forms that do not naturally exist anywhere on Earth. Some neutron stars hide beneath thick atmospheres of carbon or hydrogen. A neutron star may have a solid surface, but that surface is not necessarily exposed directly to space. Gravity can hold a remarkably thin yet optically important atmosphere above it. Because heavier elements tend to sink rapidly, the uppermost layer can become dominated by the lightest material available. Hydrogen and helium are common possibilities, while some young neutron stars appear consistent with carbon atmospheres. The choice matters enormously when astronomers interpret the light. Different atmospheric elements shape the outgoing spectrum in different ways, changing estimates of the star's temperature and apparent size. A blackbody model can therefore give misleading results if the atmosphere is ignored. Researchers compare X-ray observations with detailed models of how radiation passes through intensely magnetized plasma. In some cases, identifying the atmospheric composition helps constrain the radius of the neutron star itself. That radius is one of the keys to understanding ultradense matter. Something as seemingly delicate as a layer of gas above a collapsed star can therefore influence our best attempts to determine what lies deep inside it. Binary pulsars provided early indirect evidence that gravitational waves exist. Long before instruments directly measured gravitational waves, astronomers found compelling evidence through a pair of orbiting neutron stars. In the 1970s, Russell Hulse and Joseph Taylor discovered a pulsar locked in a tight binary system. Because the pulsar emitted precisely timed radio signals, researchers could track its orbit with exceptional accuracy. General relativity predicted that such a system should lose energy by radiating gravitational waves. If that happened, the two stars would slowly spiral closer together, and complete each orbit slightly faster. Years of observations showed exactly that behavior. The orbital period decreased at the rate predicted by Einstein's theory with remarkable precision. No gravitational wave detector had yet felt the waves themselves, but the stars were clearly losing the correct amount of energy. The discovery earned Hulse and Taylor the Nobel Prize in Physics. It was a beautiful example of astronomy testing fundamental physics through natural objects. Two collapsed stars became a cosmic laboratory, revealing an invisible form of radiation decades before humanity developed technology sensitive enough to detect it directly. Merging neutron stars can produce brief bursts of gamma-ray light. For years, astronomers suspected that short gamma-ray bursts came from compact objects colliding. The idea became dramatically stronger when gravitational waves from a neutron-star merger were detected in 2017. Less than 2 seconds after the gravitational signal, satellites recorded a short burst of gamma rays from the same general region of sky. Telescopes then found a rapidly changing optical source in a nearby galaxy. For the first time, different kinds of cosmic messenger had traced the same event. The gamma rays are thought to arise from an ultra-fast jet launched after the merger, although exactly how that jet forms depends on the object left behind and the surrounding debris. Because the beam is narrow, many mergers will not point directly toward Earth and may appear very different. That explains why gravitational wave observations are so valuable. They can reveal collisions that gamma-ray telescopes might miss. A flash, lasting only a couple of seconds, can therefore mark the instant when two neutron stars finish an orbital dance that may have lasted billions of years. The first observed neutron-star merger transformed gravitational wave astronomy. On August 17, 2017, gravitational wave observatories detected a signal unlike the earlier black hole mergers. It lasted much longer and matched two neutron stars spiraling together. Astronomers rapidly shared the location estimate with observatories around the world. Within hours, telescopes found a new source of light in the galaxy NGC 4993. Over the following days, nearly every major branch of astronomy joined the investigation. Radio telescopes, optical instruments, and X-ray observatories tracked different parts of the aftermath. The event became known as GW 170817. It marked the beginning of truly multi-messenger gravitational wave astronomy because information arrived through both spacetime vibrations and electromagnetic radiation. Researchers used the observations to test the speed of gravity, study heavy element production, and investigate the behavior of ultradense matter. The event also provided an independent way to estimate cosmic distances. One collision suddenly connected fields that had often worked separately. It demonstrated that gravitational waves were not merely new signals to detect. They were a new way to coordinate our view of the universe. Kilonova explosions reveal newly forged heavy elements through changing colors. After two neutron stars collide, radioactive debris thrown into space can create a transient glow called a kilonova. It is much fainter than a typical supernova, yet its rapidly changing color carries remarkable information. Freshly created heavy nuclei are unstable and begin decaying almost immediately. That radioactive decay heats the expanding material and powers the light we observe. But first, some kilonovae can appear relatively blue. As the debris expands and its composition becomes more influential, the emission may shift toward red and infrared wavelengths. Elements known as lanthanide are especially important because their complex atomic structures make the ejecta highly opaque to visible light. By tracking this color evolution, astronomers can estimate what kinds of nuclei were produced and how much material escaped. The kilonova observed after the neutron star merger in 2017 gave powerful support to this picture. Its changing light allowed researchers to watch nuclear physics unfold across another galaxy. Colors lasting only days revealed an element-making process that had been predicted for decades. Platinum may be created alongside gold during neutron star collisions. Gold attracts attention, but it is only one member of a much larger family of heavy elements that can emerge from neutron-rich cosmic debris. Platinum is another. During a neutron star merger, nuclei can absorb neutrons in rapid succession before radioactive decay has time to pull them back towards stability. This process allows matter to climb into regions of the nuclear chart that ordinary stellar fusion cannot easily reach. As unstable nuclei later decay, they populate a range of stable heavy elements that includes platinum group metals. The exact proportions depend on the density, temperature, and neutron richness of the ejected material. Different parts of the merger can therefore manufacture different mixtures. Scientists compare theoretical predictions with kilonova observations and with the abundance patterns measured in ancient stars. Those old stars preserve chemical evidence from earlier generations of cosmic events. Platinum on Earth was incorporated into the material that formed the solar system long after its atoms were made. A metal prized for resisting corrosion may owe its existence to matter that was once violently expelled from colliding stellar corpses. Neutron star mergers can leave either magnetars or black holes behind. The collision is not necessarily the final chapter of a neutron star merger. What remains at the center depends strongly on the combined mass and on the properties of ultradense matter. If the merged object is too heavy for any neutron star to support, it can collapse almost immediately into a black hole. In other cases, rapid rotation may temporarily help resist gravity. The remnant can survive for milliseconds, seconds or perhaps much longer before eventually collapsing. If its mass remains below the relevant stability limit, it could persist as an extremely massive neutron star with an intense magnetic field. Such an object may behave like a newborn magnetar. These different outcomes matter because they change the surrounding explosion. A long-lived central remnant can inject additional energy into the expanding debris, while rapid black hole formation may produce a different pattern of radiation. Astronomers try to infer the outcome from gravitational waves, gamma rays, and later emission. Each merger therefore becomes a test of the maximum mass that neutron star matter can withstand before gravity wins completely. Dense stellar collisions can launch jets moving almost as fast as light. Some of the most spectacular structures created by compact object mergers are narrow jets of matter moving at relativistic speeds. To launch one, material falling toward the central remnant forms a hot, rotating disk. Powerful magnetic fields can thread that disk and the object at its center. Under favorable conditions, energy is channeled along the rotation axis and drives a tightly focused outflow. The particles in the jet can move so close to light speed that relativistic effects dominate what observers see. Radiation becomes strongly concentrated in the forward direction, and time intervals measured by distant telescopes can appear compressed. The jet must also force its way through debris expelled during the collision. If it succeeds, it can produce high-energy emission and later create a widening afterglow as it slams into surrounding gas. The structure is not always a simple, uniform beam. Observations suggest some jets possess energetic cores surrounded by slower material. By watching the afterglow brighten and fade, astronomers can reconstruct the geometry of an explosion that occurred far beyond direct resolution. Relativistic jets appear brighter when they point almost directly toward Earth. Orientation can completely change how an extreme cosmic event looks. When material in a jet moves close to light speed, relativity concentrates much of its radiation in the direction of travel. An observer positioned near the jet axis therefore sees a source that appears far brighter than someone viewing the same event from the side. This effect is called relativistic beaming. It helps explain why some active galaxies look extraordinarily luminous and why gamma-ray bursts can be visible from immense distances. The underlying source does not radiate equally in every direction. Geometry determines whether Earth lies inside the narrow cone of enhanced emission. Motion also changes the observed timing. Variations can appear faster because photons emitted later along the approaching jet have less additional distance to travel toward us. The opposite jet may look much fainter because its radiation is beamed away. Astronomers must account for these effects before estimating the true power of the source. Sometimes the difference between an apparently overwhelming cosmic beacon and a modest distant object is simply which direction its jet happens to face. Gamma-ray bursts are visible across most of the observable universe. A gamma-ray burst can be detected from distances so great that its light began traveling when the universe was still young. These events are valuable precisely because their brief brilliance can cut through cosmic distance. High-energy satellites first locate the burst, then ground-based telescopes race to observe its fading afterglow. If astronomers obtain a spectrum, they can measure how strongly cosmic expansion has stretched the light toward longer wavelengths. Some bursts have been confirmed at redshifts corresponding to more than 13 billion years of light travel time. That makes them potential probes of the era when the first generations of stars and galaxies were forming. Unlike galaxies, which may be faint and difficult to study individually at such distances, a burst can temporarily advertise the presence of a single dying star with extraordinary intensity. The event itself soon disappears, but its afterglow may illuminate gas along the line of sight. Gamma-ray bursts therefore provide brief beacons from epochs that ordinary telescopes struggle to examine. A stellar death can become visible across nearly the entire observable cosmos. Long gamma-ray bursts often accompany the deaths of massive stars. The connection between long gamma-ray bursts and stellar death became clear when astronomers found supernovae emerging beneath some fading afterglows. These bursts generally last longer than about 2 seconds, though duration alone does not tell the whole story. The leading model involves a massive star whose core collapses and forms a compact central object. Instead of producing only a roughly spherical explosion, the system launches narrow relativistic jets through the star. If one jet successfully punches through the outer layers and points toward Earth, we detect a powerful burst of gamma rays. The surrounding star can still explode as a broad-lined type EIC supernova after losing its outer hydrogen and helium. Not every such supernova makes a detectable burst because the jet may fail or point elsewhere. The association gives astronomers a direct link between high-energy transients and the final evolution of certain massive stars. A gamma-ray burst is therefore not simply an unusually bright supernova. It is evidence that the collapse created an organized engine capable of driving matter outward at nearly light speed. Short gamma-ray bursts usually arise from merging compact stellar remnants. For decades, short gamma-ray bursts were harder to explain than their longer relatives. They flashed for less than about 2 seconds, and often occurred far from obvious regions of active star formation. That distribution suggested older stellar systems rather than recently formed massive stars. The strongest explanation became the merger of compact remnants, especially two neutron stars. Such binaries can survive for millions or billions of years while their orbits slowly shrink. By the time they collide, they may have traveled far from the places where their original stars were born. Gravitational wave observations eventually provided decisive support for this picture. Some short bursts may also arise when a neutron star merges with a black hole. The details of jet formation are still being studied, and not every compact merger will produce a detectable burst. What makes the phenomenon remarkable is the timescale contrast. A binary can evolve almost invisibly for longer than complex life has existed on Earth, then release its most obvious signal in less time than it takes to speak a sentence. Long gamma-ray bursts often accompany the deaths of massive stars. When certain enormous stars reach the end of their lives, their cores collapse, while the rest of the star is still falling inward. Under some conditions, that collapse creates a compact central engine capable of launching two narrow jets through the surrounding stellar material. The jets move at speeds extremely close to light and can generate an intense burst of gamma radiation once they break free. Astronomers connected these longer bursts with stellar death after detecting supernovae emerging beneath several fading afterglows. The parent stars appear to have lost much of their outer hydrogen before exploding, which helps the jets escape. Yet most massive stellar collapses do not create gamma-ray bursts. Something unusually powerful must happen at the center, and the star must possess the right rotation and internal structure. Even then, a burst is detectable only from favorable directions. These events reveal that some stars do much more than simply explode. Their final collapse can build a temporary cosmic engine that channels enormous energy through the dying star before the stellar interior has finished falling apart. Short gamma-ray bursts usually arise from merging compact stellar remnants. A burst lasting less than a few seconds can be the final signal from a binary system that survived for billions of years. Compact remnants, such as neutron stars, may begin far apart and gradually spiral together as their orbit loses energy. The process is extraordinarily slow at first. Near the end, however, everything accelerates until the two objects collide. In some cases, the merger produces a tightly focused jet that emits a brief pulse of gamma radiation. Short bursts were mysterious for decades because their host environments often differed from the star-forming regions associated with long bursts. Many appeared in older stellar populations, which matched the expectation for binaries that take a long time to merge. The decisive breakthrough came when gravitational waves from a neutron star collision were followed almost immediately by a short gamma-ray signal. Some short bursts may instead involve a neutron star meeting a black hole. The family is therefore linked not to one exact object, but to the catastrophic union of stellar remnants whose original stars disappeared long before the final flash. A gamma-ray burst beam could miss Earth despite enormous nearby energy. The most important thing about many gamma-ray bursts is not simply how powerful they are, but where their energy goes. Much of the radiation is concentrated into narrow jets rather than emitted equally in every direction. That means a burst could occur comparatively nearby and still look unimpressive from Earth if neither jet points toward us. Astronomers might instead notice a supernova, a kilonova, or a faint afterglow produced as the outflow slows and spreads. This geometry creates a major observational bias. The bursts we detect most easily are the ones whose beams happen to sweep across our planet. For every event aimed toward Earth, many others may be pointed elsewhere. Researchers tried to estimate this hidden population by studying jet opening angles and searching for explosions whose later emission becomes visible after the beam widens. The true rate of these events is therefore higher than the number of detected gamma-ray flashes suggests. Cosmic violence can occur surprisingly close by without producing its most dramatic signature in our sky, simply because the universe aimed the beam in another direction. Some gamma-ray bursts last less than the blink of an eye. The shortest high-energy flashes can begin and end before a person could consciously react to them. Satellites have recorded gamma-ray bursts lasting only fractions of a second, which forces astronomers to infer an astonishing amount of physics from a tiny interval of data. Such brevity tells researchers that the region producing the initial radiation must itself be extremely compact. A source cannot coordinate a rapid brightness change across an area larger than light could cross during that change. Millisecond structure therefore points toward engines on the scale of compact stellar remnants rather than ordinary stars. Within the burst, individual spikes may appear even faster, suggesting turbulent or magnetic processes inside an outflow traveling almost at light speed. Instruments designed to study these events must monitor the sky continuously because there is no opportunity to receive advance warning and aim a telescope. By the time an alert reaches human observers, the primary flash is already history. The shortest bursts demonstrate how the universe can release information about an enormous catastrophe in a signal briefer than an involuntary blink. Others continue radiating high-energy light for several hours. Not every gamma-ray burst fits neatly into the familiar picture of a brief flash, followed by a fading afterglow. Astronomers have discovered ultra-long events whose high-energy activity continues for thousands of seconds and sometimes much longer. Their unusual duration suggests that the central engine can remain active instead of shutting down quickly. Several explanations have been proposed. One possibility involves the collapse of an especially extended star, where material continues feeding the newly formed compact object for an unusually long period. Another invokes prolonged magnetic activity from a newborn neutron star. Researchers have also considered rare stellar disruptions by black holes for some unusual transients. Distinguishing between these possibilities requires studying the burst spectrum, post-galaxy, and later light. The long duration is scientifically valuable because it exposes the behavior of the central engine over a much greater interval than ordinary bursts allow. A phenomenon once defined by its brevity can therefore stretch across a large portion of an observing night. Extreme cosmic events do not always respect the tidy categories scientists create to describe them. Gamma-ray burst afterglows can remain detectable long after the main flash. The gamma-ray signal may disappear within seconds, but the explosion can keep announcing itself at other wavelengths for days, weeks, or even months. A relativistic outflow eventually crashes into gas surrounding the source. That collision drives a shock through the material and accelerates charged particles, which then radiate across the electromagnetic spectrum. X-rays may dominate early, followed by optical and radio emission that fades more gradually. This afterglow gives astronomers far more information than the primary burst alone. Its spectrum can reveal the distance to the event. Its changing brightness can expose the shape of the jet and the density of the surrounding environment. Sudden changes may indicate additional energy being supplied by the central engine. Radio observations can continue after the optical source becomes too faint to see. Because the afterglow evolves, astronomers often coordinate telescopes around the world to capture different stages. A gamma-ray burst is therefore not merely a momentary flash. Its collision with surrounding space creates a lingering record that can be studied long after the initial explosion has vanished. The brightest recorded gamma-ray burst overwhelmed several space-based detectors. On October 9, 2022, satellites detected an event so extraordinary that astronomers quickly gave it a memorable nickname. GRB 2210009A became known as the boat, meaning the brightest of all time. Its gamma radiation was intense enough to saturate instruments designed specifically for powerful cosmic flashes. Even detectors that were not built primarily for gamma-ray astronomy noticed effects from the event. The burst came from billions of light-years away, yet its jet happened to be directed exceptionally close to Earth's line of sight. That favorable alignment dramatically amplified its apparent brightness. Researchers studied the event across the electromagnetic spectrum and found evidence linking it to the collapse of a massive star. The burst also affected Earth's ionosphere, despite the enormous distance separating us from the source. Statistically, an event this bright in our sky may be exceptionally rare on human timescales. Its detection gave astronomers an unprecedented laboratory for studying relativistic jets, while also demonstrating how strongly orientation can transform the appearance of a distant explosion. Extreme cosmic explosions may briefly ionize parts of planetary atmospheres. High-energy radiation does not need to strike a planet physically to alter its atmosphere. X-rays and gamma rays can remove electrons from atoms and molecules when they are absorbed high above the surface. If a sufficiently energetic cosmic explosion occurs nearby, this ionization can temporarily change atmospheric chemistry. On Earth, strong gamma-ray events have measurably disturbed the ionosphere even when their sources were located far beyond the solar system. A much closer explosion could produce larger effects. Researchers model how intense radiation might alter ozone concentrations and allow additional ultraviolet light to reach the ground afterward. The severity would depend heavily on distance, beam direction, atmospheric composition, and the energy spectrum of the event. This does not mean gamma-ray bursts routinely threaten inhabited worlds. The dangerous combination of proximity and alignment should be uncommon. Still, the physics introduces a fascinating connection between stellar catastrophes and planetary environments. A world may never encounter the debris of an explosion, yet radiation alone can reach across space and temporarily change the chemistry of the air surrounding it. Distant gamma-ray bursts illuminate gas from the universe's earliest eras. A gamma-ray burst can act like a temporary searchlight behind material that would otherwise be extremely difficult to examine. When the burst's afterglow passes through gas on its way to Earth, atoms absorb very specific wavelengths. Astronomers spread the incoming light into a spectrum and identify those missing portions. Each absorption feature reveals something about material lying between the explosion and us. For very distant bursts, that material can belong to an era when the first generations of galaxies were transforming the universe. Researchers can investigate chemical abundances and measure how much neutral hydrogen remained in intergalactic space. The technique is especially powerful because a burst can briefly outshine its host galaxy by an enormous factor. Unlike quasars, these sources do not remain active for millions of years, so they probe environments associated with individual massive stars. Catching them requires speed because the useful light fades rapidly. For a short period, however, the death of one remote star can backlight billions of light-years of cosmic history and expose matter that would normally remain almost invisible. Astronomers use fading afterglows to locate otherwise invisible cosmic explosions. The initial gamma-ray detection often tells astronomers only that something happened within a broad patch of sky. To learn where the event actually occurred, they hunt for its rapidly fading afterglow. X-ray telescopes can narrow the position first. Optical observatories then search for a new point of light that was absent from earlier images. Once the source is identified precisely, astronomers can determine whether a host galaxy lies beneath it. That step can transform an anonymous burst into a physical event with the distance and environment. Sometimes the host is astonishingly faint and becomes visible only after the afterglow has nearly disappeared. In other cases, the explosion occurs well outside the brightest region of its galaxy, offering clues about the object that produced it. Researchers compare images taken at different times to separate the transient from constant background sources. This pursuit has turned fading light into a form of cosmic detective work. The explosion itself may be impossible to resolve directly, but its disappearing afterglow points back toward the exact place where the catastrophe occurred. A tidal disruption event begins when a star approaches too closely. Most stars can orbit a massive black hole safely for immense periods, provided they stay far enough away. Trouble begins when an unlucky orbit carries one inside the black hole's tidal radius. At that distance, the changing gravitational pull across the star becomes stronger than the star's own ability to hold itself together. The critical distance depends on both objects. A larger star can be disrupted farther out, while a denser star may survive a closer approach. The star may have reached this dangerous orbit after gravitational encounters with other stars altered its path over millions of years. Nothing needs to strike the black hole directly. The encounter is purely gravitational. Once disruption begins, the star's previously orderly structure rapidly unravels, and its material follows a range of new trajectories. Astronomers search galactic centers for the resulting flares because many central black holes are normally inactive. A single misplaced star can suddenly reveal an object that had remained almost completely dark despite outweighing millions of suns. Black hole gravity can stretch a doomed star into a long stream. Near a black hole, gravity changes significantly over surprisingly short distances. During a close stellar encounter, the side of the star facing the black hole feels a stronger pull than the side farther away. At the same time, the star is squeezed in directions perpendicular to its orbit. The combined deformation can stretch the star into an extraordinarily elongated stream of gas. This process is sometimes called spaghettification, although the underlying physics is the more precise idea of tidal force. The star's original spherical shape disappears as different regions acquire different orbital energies. Some gas races ahead, while other material trails behind. Computer simulations show streams wrapping around the black hole before colliding with themselves and beginning to circularize. Those collisions convert orbital motion into heat and help build an accretion flow. What began as an intact star can therefore become a structure extending far beyond its original diameter. The destruction is not caused by the black hole touching the star. Gravity alone pulls different parts of the same object onto radically different paths. Only part of a shredded star may fall into the black hole. Being torn apart by a black hole does not necessarily mean every piece of the star is consumed. During disruption, different portions of stellar material receive different amounts of orbital energy. Roughly speaking, some debris becomes more tightly bound to the black hole, while some receives enough energy to escape. The bound material travels away on elongated paths, before returning toward the point of closest approach. Its return rate strongly influences how the resulting flare evolves. The unbound fraction heads outward instead and can eventually mix with gas in the galactic nucleus. Exactly how much is captured depends on the geometry of the encounter and the star's internal structure. This division produces one of the strangest outcomes imaginable. A black hole can destroy a star completely without actually eating the whole thing. The event transforms the star into separate populations of debris with entirely different futures. By measuring the changing luminosity of tidal disruption flares, astronomers try to infer how rapidly the bound material falls back. The star disappears as a coherent object, but much of its substance can survive the encounter. Escaping stellar debris can be flung back into interstellar space. The material that avoids capture during a tidal disruption does not simply remain parked beside the black hole. Some of it can leave the encounter traveling at tremendous speed. Because different parts of the original star require different energies, unbound gas may be launched outward from the galactic center on trajectories that never return. The escaping stream carries elements that once belonged deep inside a star and can eventually collide with surrounding interstellar material. Those interactions may generate shocks and radio emission long after the brightest phase of the disruption. Researchers are studying whether such debris could contribute meaningfully to the unusual environments around central black holes. Its chemical composition also contains information about the destroyed star. If deeper stellar layers become exposed, spectra might reveal products of nuclear processing that would normally remain hidden inside the star. A tidal disruption event, therefore, does more than feed a black hole. It can redistribute stellar material into its host galaxy. One close gravitational encounter separates the star into matter destined for darkness and matter thrown outward into a completely new existence. Tidal disruption flares can reveal black holes inside otherwise quiet galaxies. Many galaxies contain massive central black holes that are remarkably difficult to detect. If little gas is falling inward, the black hole produces almost no radiation of its own. It may sit dormant for centuries or much longer while stars orbit nearby. Then, one star wanders into danger. The resulting disruption supplies a sudden reservoir of material, and the galactic nucleus brightens dramatically. Astronomers can discover these flares through optical surveys, ultraviolet telescopes, or X-ray instruments. The light usually evolves over months rather than remaining constant like a persistently active galactic nucleus. That temporary behavior helps identify the event. Once recognized, the flare can provide information about the mass of the central black hole and the physics of matter falling toward it. This technique is especially useful in galaxies where ordinary observations give little evidence of nuclear activity. A black hole that cannot be seen directly may therefore expose itself through a single unlucky star. For astronomers, the victim becomes a beacon, announcing the presence of an otherwise hidden gravitational giant. Some shredded stars produce powerful jets aimed across intergalactic space. Most tidal disruption events glow because stellar debris heats as it settles around a black hole. A rare few do something much more dramatic. They launch relativistic jets from the galactic center. One famous example was discovered in 2011 when a source named Swift-J 1644+57 erupted in X-rays and remained violently variable. The leading explanation was a star being disrupted by a massive black hole, while a jet happened to point roughly toward Earth. Exactly how such jets form is still under investigation. Strong magnetic fields threading the newly created accretion flow are probably important. The jet can transport energy far beyond the immediate region of the destroyed star and generate radio emission as it encounters surrounding gas. Because relativistic beaming greatly enhances a jet viewed head-on, only a small fraction of jetted disruptions should look spectacular from Earth. These events combine two extremes in one system. A star is torn apart by gravity. Then some of the energy released by its destruction is channeled into matter moving almost as fast as light. A black hole may repeatedly strip matter from the same surviving star. Not every close encounter ends with total destruction. A star can pass near a black hole, lose only part of its outer layers, and then escape on a highly elongated orbit. If that orbit remains bound, the star eventually returns. Each close passage can remove more material and create another flare. Astronomers have identified repeating nuclear transients that may be produced by this partial tidal disruption process. Their recurrence offers something rare in transient astronomy. Instead of seeing a catastrophe only once, researchers may watch the same star return to danger again and again. The timing between outbursts provides information about the surviving orbit, while changes in brightness can reveal how the star is evolving after each encounter. Repeated stripping may eventually destroy it completely, or alter its structure enough to change the pattern. In some scenarios, only the star's extended envelope is vulnerable while its denser core survives. A black hole can therefore behave less like a single fatal trap and more like a gravitational machine that removes pieces of the same star over successive passages. White dwarfs can also be torn apart by intermediate-mass black holes. A white dwarf is extraordinarily compact, so an ordinary supermassive black hole may swallow it whole before tidal forces can destroy it outside the event horizon. A smaller black hole changes that calculation. Intermediate-mass black holes are thought to occupy the gap between stellar mass objects and the giants found in galactic centers. If one encounters a white dwarf, the tidal radius can lie safely outside the horizon. The compact star may then be pulled apart before crossing the point of no return. The encounter could compress and heat the white dwarf strongly enough to trigger nuclear burning in some circumstances, potentially producing an unusual explosive transient. Detecting such an event would be exciting for another reason. Intermediate-mass black holes have been notoriously difficult to confirm. A disrupted white dwarf could provide a distinctive sign of their existence in dense star clusters or dwarf galaxies. The victim's density effectively becomes a measuring tool. Only a black hole within the appropriate mass range can tear this kind of stellar remnant apart where the destruction remains visible. Tidal forces grow dramatically across the event horizon of smaller black holes. The event horizon is famous because nothing inside it can escape, but the experience of approaching that boundary depends strongly on the black hole's mass. For a stellar mass black hole, the horizon is relatively small. Gravity therefore changes very rapidly across the length of a human body or any other extended object near it. The resulting tidal forces can become destructive before the horizon is reached. Around a supermassive black hole, the situation is surprisingly different. Its horizon is much larger, so the gravitational gradient at the boundary can be far gentler. An object could theoretically cross the horizon of a sufficiently massive black hole without being immediately torn apart at that exact location. Destruction would still follow deeper inside. This distinction reveals why black holes cannot be understood by surface gravity alone. The important quantity for stretching an object is how quickly gravity changes from one point to another. Smaller black holes can therefore be more violently disruptive near their horizons than far heavier ones, despite possessing dramatically less total mass. Supermassive black holes can swallow stars before tearing them apart outside. There is a point where making a black hole more massive actually makes visible tidal disruption less likely. As the black hole grows, its event horizon expands faster with mass than the tidal disruption distance does. Above a certain scale, a sun-like star can cross the horizon while still largely intact. Any later destruction occurs where its light can never escape. Astronomers sometimes call the approximate dividing mass the Hill's mass, although the exact value depends on the star and on whether the black hole is spinning. Spin can change the size and geometry of the relevant boundaries, allowing disruptions around somewhat heavier objects in certain orientations. This creates a useful observational clue. If astronomers confidently identify a tidal disruption flare from a very massive galactic nucleus, the event can potentially constrain the black hole's properties. The absence of flares at the highest masses also has a physical explanation. The black hole has not become too weak to destroy stars. Its horizon has simply grown so large that the crucial destruction disappears from the observable universe. Merging black holes radiate several suns' worth of mass as gravitational waves. During the final moments of a black hole merger, an extraordinary fraction of the system's mass can leave without becoming matter or light. Einstein's equation linking mass and energy allows part of the total mass to be converted into gravitational radiation. In the first directly detected merger, the two original black holes had masses of roughly 36 and 29 suns. The final black hole contained about 62 solar masses. Around 3 suns' worth of mass had effectively been carried away as gravitational wave energy. The conversion occurred mainly during the violent final stage of the collision. For a brief moment, the power emitted in gravitational waves exceeded the combined light output of the visible universe, even though the event itself may have produced almost no light. This does not mean 3 actual stars were destroyed. Mass already present in the orbiting black holes was converted into energy through the changing gravitational field. Measuring that missing mass lets physicists test numerical predictions of general relativity under some of the strongest gravitational conditions nature provides. The final black hole can recoil from its galaxy after merging. A newly merged black hole does not always remain exactly where the collision occurred. Gravitational waves can carry momentum as well as energy. If those waves are emitted more strongly in one direction than another, the final black hole must move the opposite way to conserve momentum. This gravitational recoil is often called a kick. Simulations show that some configurations can produce velocities of thousands of kilometers per second. In smaller galaxies, a sufficiently strong kick could launch the black hole completely out of the system. A weaker recoil might leave it oscillating through the galactic center before eventually settling again. Astronomers search for possible examples by looking for active black holes whose positions or velocities differ from those of their host galaxies. Confirming a recoiling supermassive black hole is difficult because other processes can imitate some of the same signatures. Yet the predicted effect is a remarkable consequence of wave emission. 2 invisible objects can merge, send space-time ripples unevenly across the cosmos, and propel the resulting black hole through space like an enormous gravitational rocket. Unequal mergers produce stronger gravitational kicks than balanced collisions. The strength of a recoil depends on how asymmetrical the merger becomes. If 2 identical non-spinning black holes approach in a perfectly symmetric configuration, their gravitational wave emission can balance so that little net momentum is carried away. Change the masses, however, and the symmetry breaks. One black hole moves differently from the other, creating a more uneven radiation pattern and a larger kick. Spin can amplify the effect dramatically, especially when the two spin directions are arranged unfavorably relative to the orbit. Numerical relativity simulations explored these configurations by solving Einstein's equations on powerful computers. They show that the most extreme recoils require particular combinations of spin and orbital geometry, rather than mass difference alone. Understanding these kicks matters for galaxy evolution. Small early galaxies may have struggled to retain growing black holes if mergers frequently launched the remnants away. The black holes seen at the centers of massive galaxies today therefore carry a hidden history of which mergers they survived. A slight imbalance during a collision can influence whether a galactic nucleus keeps its central black hole at all. Some recoiling black holes may wander far beyond their galactic centers. If a merger gives a black hole a substantial kick without ejecting it completely, the object can begin a long journey through its host galaxy. Instead of sitting in the nucleus, it may travel thousands of light years away before gravity turns it back. Repeated passages gradually lose energy through interactions with surrounding stars and matter, eventually drawing the black hole toward the center again. The process can take a very long time. During its wandering phase, the black